So our next speaker, his name is Yunlong Jiang, and he's from the Huazhong University of Science and Technology. And he will provide a talk on LET VINS, a hybrid optical flow method with a lightweight CNN network in ICCV2023 Visual Inertial SLAM Challenge. So welcome to the Yunlong Jiang and to provide his talk. I will stop share my screen and give the stage to Yunlong Jiang.
Okay, thank you. Okay. Dear ICCV SLAM Challenge Committee and fellow participants, we are honored to have achieved second place in this competition. And it is my great pleasure to participate in ICCV SLAM Challenge seminar on behalf of our team and share the method we used. We are a team from State Key Laboratory of Intelligent Manufacturing Equipment and Technology at Huazhong University of Science and Technology. Our team members include Yunlong Jiang, Yicheng Lin, and Bin Han. The method we propose is called LET VINS, a hybrid optical flow method with a lightweight CNN network. My presentation is divided into these 4 parts, and I will start with introduction. Before we introduce our proposed new optical flow method, let's first review the visual inertial odometry, VIO, and the visual inertial navigation system, VINS. VIO is a technology that estimates the pose and motion of a camera by analyzing camera image data, often combined with data from inertial sensors to improve accuracy. VINS further integrates inertial data, allowing us to position and navigate more accurately. Due to its numerous advantages, VINS is currently one of the prominent VIO frameworks. The VINS framework usually includes modules such as feature extraction and matching, visual inertial state estimation, and back-end optimization. A full pipeline of VINS system framework is shown in this picture. By working together through these steps, the system can achieve high precise navigation and positioning. An important module among them is the optical flow method, which helps analyze the pixel displacement in the image to understand the motion of the camera. But the robustness of real-time optical flow in high dynamic range has not yet achieved ideal performance. Traditional optical flow methods make the assumption of brightness consistency. These methods are highly efficient, but their applicability is limited, especially in scenes with dynamic illumination. End-to-end optical flow methods use conventional networks to extract optical flow information between image sequences directly. These methods yield excellent results, but come with low efficiency. The existing optical flow methods cannot balance the performance and efficiency in real-time applications. So we propose a hybrid optical flow method, which combines the feature extraction ability of convolutional network with the efficiency of traditional methods. In the second part, I will talk about the hybrid optical flow method we proposed. In this section, we first introduced the network architecture. The figure shows the complete structure of the network used in real time during SLAM. As shown in this picture, the network is designed to be as lightweight as possible. The image is first processed through a shared encoder, producing a 16-channel intermediate representation, which is then passed to the decoder, where it is separately converted into single-channel scores and 3-channel feature maps. Then we introduced the optical flow with convolution feature maps. On the score map, corners that are easy to track are extracted using a method similar to good feature to track. A Gaussian image pyramid is constructed using the feature maps, and the LK pyramid optical flow method is employed to calculate optical flow. With fewer layers and a smaller convolution kernel, the feature map contains less high-level semantic information while retaining more low-level image information. We believe that the low-level information is sufficient for our tasks. Therefore, the computational complexity of the designed network is much lower than the other ones. The third part is learning track corners and invariant feature. In this section, we introduce our model training method. The network training process is shown in this picture. A shallow network is first used to extract the score map S and feature map F. Then, in order to supervise the reliability of the training corners, a deep convolution is used to extract the dense descriptor map D. Finally, we calculate the corner loss and matching loss based on the results of S, F, and D. Based on the work of alike, we also use the reprojection loss function, PK loss function, and reliability loss function. In addition, for the problem of fast convergency to straight edges when extracting corners, we propose a line PK loss based on the idea of hard sampling mining. The NRE loss function for calculating global features is combined with a local mask to obtain a loss function that only considers local invariance, which we call MNRE. To verify the performance of the proposed flow in dynamic lightning scenes, we continuously track the position of the extracted feature points in a sequence with an active light source. The right picture shows that the proposed method can continuously track feature points in scenes with illumination changes. The traditional optical flow method fails due to the interference of the active light source, resulting in a rapid increase in the rejection rate. The proposed method simultaneously extracts feature map F and score map S using a lightweight network. Convolution features are advanced information beyond the original RGB image with some illumination and perspective invariance. Points with higher invariance are considered corners, and these are assumed to be more stable in the optical flow. As shown on the left picture, the proposed optical flow can maintain stable corner tracking under the dynamic lightning conditions. Based on the assumption that the convolution features of the same pixel in two images are invariant, we combine the traditional pyramid LK algorithm to form the robust hybrid optical flow method. As shown on the right, the proposed hybrid optical flow method can improve the robustness of the SLAM system in dynamic lightning scenes. The fourth part is experiment results. We compare the results obtained by VINS using loop detection, our method without loop detection, and our method using loop detection. Comparisons of three typical trajectory results are shown in those pictures. The results are summarized in table 1, indicating that our proposed method achieved high level of accuracy, even without the use of loop detection. The accuracy of the results is relatively high. By replacing the original corner extraction algorithm and the optical flow calculation method, the modified VIO system performs well in dynamic lightning environment. Finally, we introduce our future work. Due to the implementation of multi-threading technology from the NCNN library, the CPU usage is relatively high. In further work, the computational effort will be reduced by 5 to 10 times. We invite you to keep an eye on our progress and updates at our GitHub repository. Your continued support and feedback are highly valued. My presentation concludes here. Thank you for listening.
Okay, thanks so much for the great talk from the Yunlong Jiang. I think this is very nice and present very detailed about your solution, and also how did a lot of the very good quantitative analysis on our data set. So currently, I would first give this opportunity to our audience. So does anyone has questions for the Yunlong Jiang? And if you have questions, and you can speak right now.
Hello, I have one question. Can you hear me?
Okay, cool.
I want to know how about the running time of your solution?
Thank you for your questions. Can you hear me right?
Yeah, we can hear you.
Oh, okay. Thank you for raising this question. It's a crucial aspect, and we are delighted to have the opportunity to address it. First, the CPU we used is CPU i7-10700, and the running time of each module is shown in the table above, including the average processing time of the feature tracker module, the motion estimator module, and the post graph module. And besides, the picture below illustrates the results obtained from running the top command, displaying the CPU utilization rates for each module during operation. And it is important to note that we employed multiple cores for computation. And because of the multi-threading capabilities of the NCNN library, this led to a relatively high CPU utilization. And that's our answer.
Okay, thank you.
Okay. I have one question. So did you notice any difference? Maybe this is a question I'll also ask for other teams. So did you notice any difference when you run your algorithm on the Titan Air dataset and the subteam Mars dataset? So do you add some specific strategy and to cope with these two different datasets from simulation to real world?
Thank you for raising this question. In our evaluation of the Titan Air and sub-TMRI's datasets, we did observe distinct differences in the performance of our system. The real-world dataset outperformed the simulated dataset, and we think the key point is motion smoothness. That is, in the real-world dataset, the real-world dataset tends to exhibit smoother motion patterns compared to the simulated dataset. And the smoother motion allows the VIO system to better estimate camera poses. So it will result in an improved performance. And
okay, got it. Okay, thank you so much for your great talk, for your work, and we are very excited for some deep learning method could be runnable on our dataset, and I think this is a very great work. And okay, I think let's move to our next speaker, and let me share my screen again.